On video, start. Hello.
Doktor,
Hmm.
saya tak boleh share screen.
Try again.
Okay.
This is group number
5.
topic A, B, C, D.
A.
Okay. Share slides. On video, please. Can you share?
Wait, doctor.
Hello, Doctor. Can you see my screen, Doctor?
Okay.
All right. Okay. So we're gonna start from here.
Okay.
All right.
Okay.
So we are from Group 5, Control System Design, and today we are presenting our assignment. My mate will introduce the group members and the outline of the project.
Okay, so good morning, Prof, and everyone. So we are from Group 5, and today we are going to present our project titled Analysis and Control of in an Industrial Hydraulic Actuator, which is Model A. And I'm Shupeke, and my teammates Muhammad Asif, Anis Farisha, and Malek Anas. Okay, so next I'll pass to Anis Farisha to talk about the introductions.
Okay, so for our model, we use electro-hydraulic actuators, where it is usually used in automotive, robotics, aircraft, industrial machine, and also known for fast response and high output. So to understand and control the system effectively, we need a good mathematical model, where we use system identification to create a dynamic model to measure the input-output data. So for system identification procedures, first we collect data collection and apply known input signals and measure the output response. And from there, we will estimate the model parameters using algorithm. And for model validation, we compare the model output with actual system to verify the accuracy. And for MATLAB, we use a MATLAB and system identification toolbox and Simulink to validate and simulate the data. So after we get the model, we use PID controller that to help improve system response and reduce steady state error. And PID tuning is done based on the identified model for better accuracy. So next, so our problem statement is the EHA are widely used in industries because of their fast response, but they are difficult to control due to their complex behavior and they doesn't behave in a linear way. So this challenge make it hard to build an accurate model. So Therefore, we came with a proper modeling and control strategy to improve system performance and reliability. Uh, I will pass to Malik.
Malik, I think you didn't open the mic.
All right, can you hear me now?
Okay.
Okay, all right. So for the objectives, we have multiple objects. First, to analyze the stability of unity feedback using root locus and board plot techniques. We also one of the objectives also is to observe how changes in the feed-forward gain can influence the system stability. Also to compute the interstability margins, gain and phase. Also to compare time domain and frequency domain analysis results. And finally, to model the hydraulic actuator system and design a PID controller for fast, accurate, and stable response. So for the scopes of the project is to use this transfer function given below under consideration for a unity feedback control system. Also to analyze the stability and performance through root locus and board plot techniques. And finally, to analyze the open and closed loop configurations for various gain values for various gain values. So for the limitations, we are going to assume that the system behavior and is a linear, and it doesn't count for nonlinear effects or time delays. So it would be like the professional case. We also one of the limitations also is the plant model would be idealized, and the frequency range in board plot analysis is bounded by practical simulation constraints. So I'll pass to my mate to talk about the methodology for modeling and analysis flow.
Who's next?
Afif?
Babe.
Oh, sorry. For methodology, for step 1 is system modeling, which is we define the open loop transfer function GS, and after that we configure the system in unity feedback form with feed forward gain K. And for step 2, which is time domain analysis, which is root locus, we need to plot the root locus of the open loop system of varying values of K. And next, we identify the critical values of K that cause the system poles to cross into the right half plane instability. And after that, discuss how poles position relate to transient performance, which is damping, overshoot, and stability. And step 3 is frequency domain analysis, which is of open loop bot plot. We select appropriate values of K based on the root locus, and then we generate the open loop bot plot. After that, we determine the three properties, which is gain margin, phase margin, phase margin, and frequency again, and phase crossover points. After that, we analyze the system robustness and stability margins. Next, and step 4, step 4 is frequency domain analysis for closed loop bot plot, which is we use the same values of K to generate closed loop transfer function, and then we plot the bot plot of transfer function, determine the magnitude peak, frequency peak bandwidth, and after that we relate frequency response characteristic to domain time behavior. And the step 5 is cross domain validation, which is we compare time domain result with frequency domain matrix, and after that we confirm the consistency of stability assessment across both domains. Next.
Okay, so I will talk about the methodology for the root locus and Simulink. So the step 1 is define the controller specifications, where our desired performance is fast response, less than 10% overshoot, a stable system and a zero steady state error. Next. Then the step 2 is the root locus design for PD and PID. So first we use the open loop transfer function, which is GS, and then we apply the root locus technique in MATLAB. So for PD controller, we add a 0 to shift the locus left, and then we choose KP and KD to place the desired 0. Then for PID controller, we add a pole at origin, which is the integral action, and we tune the KI to reduce the steady state error. So step 3 is we do the simulate in Simulink. So first of all, we build the Simulink block to construct a closed loop system. Then we add the PID controller block and input gains. Then we use a step input to observe the rise time, settling time, overshoot, and the steady state error. Next. So last but not least, we compare the PD and PID response. So we show both time response and discuss the improvement of PID over PD, where it should be have a lower error, better damping, and higher accuracy. Next. So I will pass back to Anis.
Okay, so for task 1, we are required to choose our poles and zero. So we decide to choose 2 for our poles and 0 for zeros. And our best fit percentage we got here is 80.36%, where it is acceptable since it is above 18, so it is considered good. Where in real life, the missing 19% 0.64 probably due to simplifying some components, ignoring small disturbance, or not perfectly capturing all the systems non-linearities. So next slide. So this is our step response. So our rise time here we got 0.299, settling time 0.523 second, where we have no overshoot and oscillation. The system is stable and smooth response. Uh, so for our root locus, we decide to choose our damping ratio is 0.707, which is good, and our gain K is 2.32. So the poles we have here is complex numbers, which is a real and imaginary part, uh, which means the system is under damped. So the natural frequency is 90.1, showing the system response is quiet fast. So our frequency response, uh, we can from our gain margin and phase margin, we confirm stability and the system is stable with good damping. So next slide. Okay, so for task 2, um, we perform well at gain K 2.32 with good balance between speed and stability, and we use a ideal damping ratio for most system, which is 0.707. Um, so next slide. Oh, this is our open loop transfer function and closed loop transfer function equation. Next. So this is our step response. Uh, our step response. The same one with task 1. Before we apply gain K 2.32. Okay, next slide. Okay, so this is our root locus after we multiply to K 2.32, where the roots move further to left, shows the increase in stability. Next slide. Okay, so this is our new parameters, where the rise time, settling time we got decreased. It shows a faster response and more efficient for the systems. And the overshoot we got here is 40%, which is acceptable since it is below 10%. And the steady state error is 0.002, which is acceptable. So from our pole zero map, the system poles are on the left hand side, which is the system is stable. Um, all poles are real, no imaginary part, so the system is over them. So next.
Stop. Stop.
Huh?
Anis, in your system, how many poles and how many zeros in your model?
Uh, 2 poles and 0 2 and 0, doctor.
Two,
2 poles, 0 zeros.
2 poles, 1 0.
0, doctor.
2 poles, 1 0.
Oh,
Tak, you punya model ni how many poles, how many zeros?
Zero
2
zeros.
0.
2 0,
Two poles, zero zeros.
2 poles, 2 0.
No, no zeros.
Oh, 2 poles, no zeros.
Yeah.
Second order system.
Yeah.
Malik, what is the best fit of the model? Best fit percent.
The is 4%. Is it
How many percent?
86%, doctor?
86%. Correct.
Yes.
Shupeki.
If not mistaken, I think it's 80.36% or plus minus.
80.3.
Yeah, I think it's 80 point something.
You cannot achieve 90%.
Actually, we can find more than that, but the time response of the system will be very weird.
Weird.
Yeah, the graph looks weird.
Continue.
So we
Continue.
okay, continue.
Okay, so next, so this is our Simulink model to validate our graph that we got from MATLAB code. So the graph is same with the step response generated in MATLAB. So does the value of the parameters. Okay, so I will pass to next member for class 3.
Okay, I will continue the presentation with task 3, which is closed loop system analysis in time and frequency domain. Which is for A, we need to plot the root locus and observe the system stability with changing K. So this is the root locus from the open loops transfer function equation. We can see that you have two poles and no zeros, which is the all poles at in the left half plane. So we can observe the stability with changing of K. First at K equal to 0, the pole at S negative 8.98 exponent negative 11 and S equal to negative 27. So the system is critically stable. So for K equal to 0.95 to K equal to 1.15, poles are still real but shifting close together. So the damping ratio is 1. At K equal to 1.19, the poles become complex conjugate at S negative 13.5 plus J 2.05S. So the damping ratio is 0.989, which is under damped and still stable. For K equal to 1.23, the poles become complex conjugate at S equal to negative 13.5 minus 3.23 JS, which is the damping ratio we get is 0.973, which is still under them and still stable. So overall, the system remains in the left half plane positive for all positive values. So the system is stable for all positive values K. Next. So for B, we need to use it. You need to use appropriate value of K to obtain the open loop plot. So first we try for values K is equal to 0.00306, and we get the phase margin is positive 90 degrees at omega GM 0.0178 radian per second, which is indicate that the system is stable. And the gain margin we got is infinity dB at omega PM infinity. So we can see the system has excellent stability and they have no risk of oscillation. After that, we try to use negative value of K, which is negative 0.03. We got that the magnitude never cross 0 dB. So no PM is defined, no phase margin is defined. Also same for gain margin, which is the phase curve never touch the negative 180 degree. So no clear gain margin is defined. So in theory, it's far from instability in terms of magnitude. So for negative values of K, the system is unstable. Next. So we proceed with K is equal to 2.3, which is zeta is equal to 0.707, which is preferred in practice for balance speed and stability compared to zeta is equal to 1, which is slower. So from the board plot, we can get the phase margin, which is positive 65 at omega gm 12.3 radian per second. And the gain margin is infinity dB at omega pm infinity. So this is the best K values for open loop board plot. So next. So C is we need to use the same values for obtain closed loop board plot system. So for closed loop board plot, we can determine the magnitude peak, frequency peak, and also the bandwidth. So this is the closed loop board plot for K is equal to 2.32. So the magnitude peak we got is approximately 0 dB. And the peak frequency is 0.101 radian per second. So for the bandwidth, we can see the from negative 3 dB, it approximately 19.1 radian per second, which is a higher bandwidth is equal to how fast the system responds. So from this, the system, we can know the system is stable with no excessive resonance and no overshoot behavior. Next. So last, we need to compare the time and frequency domain. So for time domain analysis, we can see that all the poles at left half plane, which is indicate the system is stable. And for frequency domain for part B, open loop approach, we get that positive gain margin and phase margin, which is indicate stable system. And also for closed loop approach, we get low magnitude peak and high bandwidth, which is indicate stable and fast response system. So overall, we can confirm that the time and frequency domain analysis yield the same conclusion regarding system stability. So I pass to the next member.
Okay, so for task 4, we are going to design the PID controller using the root locus. So next. So our desired time response specification is a fast response, overshoot less than 10% and stable, and as well as the zero steady state error. So next. So first of all, we calculate the appropriate PD controller. So this is the calculation. So we get the new dominant pole is negative 20.3 plus J 25.22. So next. So from this one, we can calculate the new zero added, which is at negative 77.24. So next. Okay, so from the formula, we can calculate that the KD is 0.093 and the KP is 7.18. So these are the figures of MATLAB code, the open loop transfer function, and the closed loop transfer function of the PD compensator system. So next. So this is the root locus of the PD controller, where from our original open loop transfer function, which is 2 poles and 0 zeros, where the poles is at negative 27 and negative 8.98 times 10 power of negative 11. So after the PD controller design, an extra zero is added at S equal to negative 77.2. So next. So to improve the system transient response, so the PD controller was designed where we assume that our overshoot percentage is around 8% and the setting time is reduced to 2/3 of the original uncompensated system. Okay, so the KP and KD is 7.18 and 0.093 respectively, and the total gain is 14.63. So next. So this is the zoom in root locus, where the new dominant pole and damping ratio are negative 20.9 plus J 25.9, and the damping ratio is 0.68. So the overshoot percentage is around 5.43%. So next. So this is the step response of the PD controller that I designed. So the final value is around 1. So it achieved zero steady state error. And the TS new is 0.164, the TP new is 0.102, and the TR new is 0.05. So the percentage overshoot is around 9.53 from the graph. So next. So to compare the uncompensated and PD compensated system, we put both transfer function into a script to see the comparison clearly. So we can see that the time response after the PD design is faster than the original open loop transfer function. So the blue one is the uncompensated system.
Top questions. Afif.
Yes,
Afif,
Doctor. Yes, Doctor.
in the program code tu, S
Yes.
S grid bracket zeta theta bracket. What does it mean? S grid bracket zeta comma theta.
That one is comma 0.
No, Afif first. These individual questions. Individual questions. Lamanya Afif, kau fikir. Why so long? Malik. Sheikh Malik.
Yes, doctor. I can
Ah,
hear you.
from the code I don't understand. S grid bracket zeta theta.
So that's basically to plot the response of the system in the graph, as we can see here.
No, 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 no. No. Anes.
Yes, Prof.
Ah,
So squid zeta is to plot the degree of the zeta in root locus.
huh?
So squid zeta is to plot the angle of the zeta in the root locus.
Okay. Theta tu?
Uh, huh?
Theta. S
Uh,
grid
to
zeta, comma
to
theta.
zero, Doctor.
Zero.
Zero, Doctor.
Oh,
Uh-uh.
bukan theta. It's not theta.
I know.
Zero tu stands for what?
Uh, uh, origin.
Origin. Zeta stands for what?
Zeta is damping ratio.
What is the angle? Theta. What is the angle when zeta 0.627?
Angle. Angle 51.17.
How you get 51 degree?
Shift cos zeta.
Shift cos,
Cos inverse zeta.
inverse cos.
Inverse cos.
Budak. Okay, proceed. Proceed.
Okay, so for the signaling of the PD controller, we use the KP, KD that we calculated before. So we put into the PD block inside the simulating. So the N is for the to filter the noise because I tried different values when the N is smaller. There are many noise for the signal. So I put 1000. So there's almost no noise lah. Okay, so next. So this one is the graph for the simulating of PD controller. So since TS is the time required for the output to reach about 2% until 5%. So we assume the tolerance level is 2%. So and the peak value is 1. So the magnitude for the TS is 1.02 since we cannot directly find the TS like what we did in MATLAB code. So I adjust the value manually. So from the graph, when the magnitude is 1.02, the TS is 0.162 from the simulink. So next. So this one also the comparison in Simulink. So we compare the uncompensated and PD compensated graph using Simulink. So next. So this one is the graph. So the blue color is the uncompensated system and the red color is PD compensated system. So we can see that the result in the Simulink is almost the same with the result in the MATLAB. So next. So for the discussion, we observe that for PD controller, we get faster rise and settling time compared to the uncompensated system. So although there is an increased overshoot due to the added proportional action, but it's still less than 10%, so it is still acceptable. Then the system is zero steady state error. So the controller effectively improves the response and maintain the overshoot percentage less than 10%. So the PD controller is successful in enhancing the transient response of the system, but with a trade-off in overshoot. So it serves as a good first step in the controller design, but may require further tuning or the addition of integral action, which is PID, for a more demanding specification. So next. So to calculate a PID controller, we use this calculation. So we get the KD equals to 0.087, KT equals to 6.73, and the KI is equals to 0.672. So next. So this is the MATLAB code for the PID controller and the open loop transfer function and closed loop transfer function for PID compensated system. So this one is the root locus of the PID controller. So we can see that the new dominant pole is at negative 20.3 plus J 25.3 and negative 40.2 plus J 49.9. So the damping ratio are both 0.627 and the percentage overshoot is 7.96 until 7.97. So a new zero S equals to negative 0.1 and a new pole at the origin are added. So the percentage of overshoot slightly decrease. So next. So this one is the transient response of the PID controller, where it also achieves zero steady state error, and the TS new and TP new are also improved to be 0.162 second and 0.0951 second. And the overshoot is also 9.36. So next. So this one is the simulating of the PID controller, where the KP, KI, KD are also from the previous calculation, and the N is also the same. Okay, next. So this one is the graph of the simulating of PID controller. So same, we cannot adjust, we cannot directly find the setting time and peak time, so I adjust manually. So we can get the TS equals to 0.168. So next. So for the discussion, we can observe that the design PID controller, where the uncompensated system already achieved a zero steady state error, so the integral component didn't significantly affect the final value. Then the PID controller slightly reduced the overshoot compared to the PD controller, making the response smoother and more stable. And the settling time was marginally faster, and the response curve shows less oscillation. So the rise time was also slightly slower than the PD controller, but still significantly faster than the uncompensated system. So next. So this one is the comparison of MATLAB code. So next. So we compare three systems in the MATLAB code. So the blue one is the uncompensated system, the red one is PD compensated system, and the green one is the PID compensated system. Okay, so next, yeah. So this one is the comparison in the Simulink. Next. Okay, so this one is the result in the Simulink. So almost the same with the graph in MATLAB code. So next. So this one is the comparison of three systems. So for the uncompensated system, it shows a slow response and long setting time. So although the overshoot is low, which is 1.34, but the performance is sluggish and not ideal for fast system. So we designed a PD and PID. Although the PD already significantly increased the rise time and setting time, it introduced some overshoot, which is 9.53, but it still stay within the acceptable limit, which is less than 10%. And it eliminates the steady state error through the high gain, and it is very efficient in improving the system speed. So for the PID, it didn't give a significant effect to if compared to the PD system. Okay, so we suggest to use a PID tuner to get a better result. So next, I pass to Malik.
Okay, so as Said mentioned before, there wasn't a very significant difference between PD and PID controllers, so we decided to go through a tuning of PID controller. So this is a brief introduction about MATLAB tuner. It is used for a plant to gain the to tune the gains of PID controller for a plant to achieve balance between performance and robustness. It works with linearized or frequency response. It also uses system identification to estimate a linear plant model from the time domain response of a plant to an applied input. So this is the tuned results of PID controller. As we can see, we put the transient behavior and response time at the default values. At the left side, we can see the transfer function, and this is the output of the tuned values of PID controller. So comparison here. After tuning the PID controller, we can see faster raise and settling time. We have also seen an increased overshoot, but this overshoot is not significantly higher. It's only 3.53% overshoot. So also the PID tuner improved the response by reducing the raising time. So as we can see here, the raise time before tuning was 0.114 second, while after tuning it became 0.0714 second. And also the steady state reach time is almost the same for PID before tuning and after tuning. So this is all about our project. These are the references, and thank you.
All right. Very good presentation. Congratulations. Okay. So no need to resubmit. Everything okay. Very detailed, very tidy, very clear. I am fully satisfied. Thank you, and see you
Thank
again.
you, Prof.
Bye bye.
Thank you, Dr.
All right, thank you,
Thank you, Dr.
Prof. Bye bye.